Okay, now we proved Dirichlet's theorem, which proves that there exist infinitely many primes in the arithmetic progression kn plus h. And obviously we have to assume that h and k are co-prime, because this is the necessary and sufficient condition for the existence of these infinitely many primes. So firstly, I will tell you the plan of Dirichlet's theorem, and then we will prove the theorem. So in the last chapter, in the fourth chapter, we have proved this asymptotic formula, summation log p upon p over all the primes less than equals to x. This is equal to log x plus order of 1. So we have proved this formula. So we will use this formula to derive Dirichlet's theorem. So Dirichlet's theorem says this thing. Actually, Dirichlet's theorem follows from this theorem. So if k is positive and h and k are co-prime, then we have for all x greater than 1 summation over primes less than equals to x, which are congruent to h modulo k, means which are lying in the arithmetic progression kn plus h. Summation of log p upon p, this is 1 upon phi k log x plus order of 1. This phi k, this is Euler's phi function at k. So this sum is extended over all the primes less than equals to x, which are congruent to h mod k, means which are lying in the arithmetic progression kn plus h. Now this theorem implies that there exist infinitely many primes in the progression kn plus h, because the principal term on the right hand side is actually this log x upon phi k. Here phi k, this is fixed for a fixed k, and log x tends to infinity as x tends to infinity. That means as x tends to infinity, the right hand side tends to infinity. So if there exists only a finite number of such primes, then this left hand side is actually just a finite sum of the terms of the type log p upon p. And we know log p upon p, this term is less than 1. So this is just a finite sum of the terms which are less than 1, and this cannot be tend to infinity as x tends to infinity if there exists only a finite number of terms in this summation. So if there is only finite number of primes in this progression kn plus h, so this is a finite sum and the right hand side tends to infinity as x tends to infinity, it means there exist infinitely many primes in this arithmetic progression kn plus h. Now one more thing this theorem reveals, that because we know this principal term 1 upon phi k log x, this is independent of h, and we know there are phi k different residue classes modulo k, and h is one of them, because we are saying p is congruent to h modulo k, and we are taking h and k are co-prime. That means h belongs to reduced residue system modulo k. So h can have phi k different values. H belongs to reduced residue system modulo k. It means h can take phi k different values from that reduced residue system modulo k, and for each value of k in that reduced residue system, this sum remains same because this is independent of h. That means each prime, or you can say prime in each of the reduced residue classes modulo k. Basically we are saying here p is congruent to h mod k. That means all the primes which are lying in the class of h, in the reduced residue class of h. So for any value of h out of those phi k values, the primes in the reduced residue class modulo k, they make the same contribution to this term, to this principal term, because this is independent of h. So it means if we take any h here, any value of h out of the phi k reduced residue system, out of the phi k values of reduced residue system, we get the same result. That means the primes which are lying in any class, they contribute the same term here, log x upon phi k. Now throughout this theorem, we will assume that k is a fixed integer, h is a fixed integer which is co-prime to k, and we have phi k Dirichlet characters modulo k, and they will be denoted by chi1, chi2 up to chi phi k. So this is our theorem. Let us say this is equation 1. Now throughout this theorem, we will assume k is an integer, fixed integer, h is fixed integer which is co-prime to k, and the phi k Dirichlet characters modulo k are denoted by chi1, chi2 up to chi phi k, and out of these chi1 with the principal character, and we will denote for chi not equal to chi1, that means for non-principal Dirichlet character modulo k, we will write L1 chi as the sum of the series summation chi n by n from 1 to infinity, and secondly L dash 1 chi, this will be denoted by summation chi n log n upon n from 1 to infinity with the negative sign. So we will denote L1 chi and L dash 1 chi by these two series, and now we know these two series are convergent. In previous chapters we have defined three equations, equation A, equation B and C. So from these equations A and B, these two series are convergent. We have shown that these two series are convergent. That means L1 chi and L dash 1 chi, they are convergent for non-principal character chi. And one more thing we have proved in previous chapter, that L1 chi, this is non-zero if chi is real valued character. So for chi real valued character, this is non-zero. So let us prove now the Dirichlet theorem. Actually, Dirichlet's theorem, this is proved by a sequence of lemmas. So firstly, I give the plan of the theorem. I will state the lemmas, and then we will prove the theorem. So first lemma to prove this theorem is, for all x greater than 1, we have this summation log p upon p over all the primes which are congruent to h modulo k. This is 1 by phi k log x plus 1 by phi k summation r varying from 2 to phi k chi r bar h summation p less than equals to x chi r p log p upon p plus order of 1. Now in this lemma, if we prove this lemma, we will prove that this summation is equal to 1 by phi k log x plus this term plus order of 1. But in the theorem we need only this term plus order of 1. So we don't need this term. That means we want to prove this term is 0. If we prove this lemma 1, then we want to prove that this term is 0. Only then this sum is equal to 1 upon phi k log x plus order of 1, and then theorem will be proved. So let us say this equation is equation 2. That means we want to prove this sum is 0. Now in the next lemma, in the second lemma, we will prove that this summation chi r p log p upon p for any chi r, where r varying from 2 to phi k, which means for any non-principal chi, this summation chi p log p upon p, this is just order of 1. So in lemma 2 we will prove this is order of 1, which will prove theorem, Dirichlet's theorem from this lemma. And let us see how. If this is equal to order of 1, then we know chi r bar at h, this is just either 0 or it is root of unity, because we know chi r, Dirichlet characters, they take the values which are roots of unity. So mod of this chi r bar h, this is either 0 or 1, so it is always less than equal to 1. And secondly, this term is order of 1. So this summation r varying from 2 to 5k, this is sum of just constants, a number which is less than equals to 1 into order of 1, that is just a constant. So this is finite sum of a constant, that means again a constant. 1 upon 5k into constant, again the whole term becomes constant, so it can be concluded, it can be included in this order of 1 term. So this lemma will prove the theorem. So now I'll write the next step of the theorem. Now we will say that lemma 1 theorem, Dirichlet's theorem will follow from lemma 1 if we prove summation chi p log p upon p is equal to order of 1 for each chi not equal to 1. So here Dirichlet's theorem follows from lemma 1 if we prove that summation chi p log p upon p over the primes less than equals to 1, this is just order of 1 for each non-principal chi not equal to chi 1. And now we have this next lemma. Now in the next lemma we will express this summation over primes in a summation over integers. Now this sum is summation over the primes p less than equals to x. So we will convert this summation into a sum which is over the integers n less than equals to x. So in the next lemma we will prove this thing for each x greater than 2, this is lemma 2, and non-principal character chi, that is chi not equal to chi 1, we will prove summation chi p log p upon p over p less than equals to x is equal to minus L dash 1 chi summation mu n chi n upon n over n less than equals to x plus order of 1. So in lemma 2 we will prove this summation is equal to this summation. Now the difference is this is over primes, this is over integers. So if we prove this sum is equal to order of 1, then because we know L dash 1 chi, this is convergent series, and if this term becomes order of 1, then this whole term becomes just a constant, and constant plus order of 1, that can be written as order of 1. So this summation will be order of 1, and we need that summation chi p log p upon p is order of 1. That means we have to prove this sum is equal to order of 1. So we can write here lemma 2. Now let us say firstly this is equation number 3. Now lemma 2 implies lemma 1 if this summation mu n chi n upon n over n, this is just order of 1. And now this is order of 1, this will be deduced from lemma 3. So now we state firstly lemma 3. So lemma 3 says for all x and for all chi non-principal character, we have this L1 chi summation mu n chi n upon n, this is order of 1. Now in this lemma, if we prove that L1 chi is non-zero for all such chi, then since this is non-zero term, so it is a constant because L1 chi is convergent series. So if this term is non-zero, then this non-zero term into summation of this is order of 1. That means this summation is just order of 1. So if we can prove L1 chi is non-zero for all non-principal chi, then this term will be order of 1, and that we need to prove. So we can write here, if L1 chi is non-zero, then from lemma 3, summation of mu n chi n upon n, this will be just order of 1. And if we can prove this is equal to order of 1, then lemma 2 implies lemma 1, and then lemma 1 implies our required theorem. That means we have to prove only here that L1 chi is non-zero for all non-principal character chi. So firstly we write here, let nk denote the number of non-principal characters, the number of non-principal characters modulo k, obviously Dirichlet characters. Let nk denote the number of non-principal characters modulo non-principal characters chi modulo k, such that L1 chi is 0. So we have assumed that nk is number of those non-principal characters chi modulo k for which L1 chi is 0. But we want to prove L1 chi is non-zero. That means we want to prove there does not exist any such chi. That means we want to prove nk is 0. Nk is 0. Now we know if L1 chi is 0, then L1 chi bar, that is also 0, because L1 chi is sum of the series summation chi n upon n. Now if summation chi n upon n is 0, then summation chi n bar upon n, that is also 0. So if L1 chi is 0, then L1 chi bar is 0, where chi bar is conjugate of chi. And we know chi and chi bar, they are not equal whenever this chi is not real, because we can write here, since chi is not real. Now what is the reason that it is not real? Because in the previous chapter we have proved that L1 chi is non-zero whenever chi is real valued character, and we are saying nk is number of those non-principal characters for which L1 chi is 0. It means chi cannot be real valued, because we have proved already for real valued chi, L1 chi is non-zero. So those chi, they are not included in this nk. So because chi is not real, so chi and chi bar, they are different characters. So if chi and chi bar are different characters, and we know whenever L1 chi is 0, L1 chi bar is 0, that means the characters for which L1 chi is 0, they occur in pairs. So if they occur in pairs, that means nk is even. So we can write here the characters of chi for which L1 chi is 0 occur in pairs. Therefore nk is even. But we want to prove nk is 0, and that will be deduced from next lemma. So we will now state lemma 4. Lemma 4. In lemma 4 we will prove for all x greater than 1, summation log p upon p for p less than equals to x and p is congruent to 1 modulo p. This is equal to 1 minus nk upon phi k log x plus order of 1. Now this lemma 4 proves that nk is 0. Let us say nk is non-zero. If nk is non-zero, then nk is greater than equals to 2. then this 1 minus nk
ये बना सकता हूँ?
बना लो
पर इसके लिए वार्ड्स चाहिए होते हैं।
भैया से ले लो
या इसे बनाने के लिए वार्ड्स चाहिए होते हैं।
चलो उधर जाके बनाओ फटाफट जाओ
या आप मुझे कैंची भी दे दो और वार्ड्स भी दे दो।
1 minus nk sorry, if nk is non-zero then nk is greater than equals to 2 because it is even. Now if nk is greater than equals to 2, 1 minus nk, this is negative. So this principal term on the right hand side, this is negative. But on the left hand side we have sum of log p upon p, and these are all positive terms. So on the left hand side we have a positive sum, and that cannot be possible. That means nk has to be 0. So we can write this: if nk is non-zero, then nk is greater than equals to 2. Then from lemma 4, 1 minus nk upon phi k into log x, that is negative term, and so tend to minus infinity as x tends to infinity. But the left hand side is sum of positive terms, so this cannot be possible. Therefore nk must have to be 0. Let us we assume this equation to be 4 and this to be 5. Now we have lemma 5, which is needed to prove lemma 4. For non-principal character chi and for L1 chi 0, now we have this L dash 1 chi summation mu n chi n upon n over n less than equals to x. This is log x plus order of 1. So this equation will be used to prove this equation. So let us say this is 6. So this is the plan of the theorem. Now we will prove all these lemmas, which completes the proof of the theorem. So firstly we prove lemma 1. So here we start proof of the theorem with the proof of lemma 1. Now we will start with the asymptotic formula, which we have proved in the earlier chapters. So summation log p upon p, this is log x plus order of 1 over the primes p less than equals to x. Now here this sum is over all the primes p less than equals to x. Now we extract all those terms which are congruent to h modulo k. Now this extraction is done with the orthogonal relation which we have proved for Dirichlet characters. We have proved this result, that summation chi r at m and chi r bar at n, and r is varying from 1 to phi k. This is just phi k if m is congruent to n modulo k and 0 otherwise. Now this result, this Dirichlet, this orthogonal relations in Dirichlet characters, they are valid if n and k are co-prime. So if n and k are co-prime. So now we take here m is equal to p and n is equal to h. Now here we have this h and k are co-prime because we are taking n is equal to h, and n and k should be co-prime. That means here h and k are co-prime. This is given to us. Then multiply both members by p inverse log p and we take sum over all the primes p less than equals to x. Now we have here this summation is equal to phi k whenever m is congruent to n modulo k and 0 whenever m is not congruent to n modulo k. We multiply both sides by log p upon p. So we have this term chi r, because we are taking m is equal to p, so chi r at p, chi r bar at h into log p upon p. We have multiplied this term by log p upon p and then taken the sum over all the primes less than equal to x. Now it will be equal to, because we know whenever m is congruent to n modulo k, this summation is equal to phi k, and when they are not congruent then it is 0, and we are taking m is equal to p and n is equal to h. So the primes which are less than equals to x, that can be separated into two parts, primes which are congruent to h and primes which are not congruent to h. So this summation can be separated into two summations. One is primes congruent to h and other is primes not congruent to h. So for the primes p which are not congruent to h, this term is 0. So that sum becomes 0. So only sum we have left with is summation over the primes which are congruent to h modulo k, and for that primes which are congruent to h modulo k, this type of summation is just phi k, so it becomes phi k into log p upon p. Right? So now we reverse the sides of these two summations. We will write this sum is equal to this, and we will separate in this summation r varying from 1 to phi k. We will separate the principal character chi 1 and all other terms separately. We will write. So from this summation, from this step, we can write that phi k into summation p less than equals to x, p is congruent to h modulo k, of the terms log p upon p. This is equal to summation p less than equals to x, r varying from 1 to phi k. I have just written this by exchanging the sides. Chi r bar h log p upon p. Now I will separate this summation into two summations. We will isolate the term corresponding to r is equal to 1, that is the term corresponding to principal character, and that will be chi 1 at p. Now we know chi 1, which is the principal character, that takes the value 1 at each value, at each integer. So chi 1 at p, it will be just 1, because p is co-prime to k also. Sorry, p is co-prime to k, because h and k are co-prime and p is congruent to h modulo k. So if h and k are co-prime, then p and k are also co-prime. So the integers which are co-prime to k, at those integers chi 1 takes the value equal to 1. So this thing becomes 1 for the principal character. So we can write here chi 1 bar at h summation p less than equals to x, chi 1 p log p upon p. So actually this is 1, but we have not written this is equal to 1. So we have taken this term to be outside because this is independent of p and these are dependent on p, so we have taken these inside the summation. Then the rest of the term is summation r varying from 2 to phi k, chi r bar h into summation chi r p log p upon p over the primes less than equals to x. Now we will put these values. Now chi1 bar at h, this is 1 because h is co-prime to k, and chi1 at h takes the value 1, then conjugate is also equal to 1. And chi1 p, because prime is varying, p is varying over this, so chi1 p is equal to 0 unless p and k are co-prime, and when they are co-prime this is equal to 1. So in this equation, now what is the first term? So we will write the number of this equation, and the number is equation 7. So let us say this is equation 7. Now the first term on right hand side of equation 7, that is this chi1 bar h is equal to 1, so this term becomes just summation p less than equals to x chi1 p log p upon p, because here we are taking p less than equals to x, not p congruent to h modulo, so that's why we cannot put the value chi1 p is equal to 1. So this is summation p less than equals to x log p upon p minus summation p less than equals to x, p divides k log p upon p. Actually we know chi1 p is equal to 0 whenever p and k are not co-prime. So whenever p and k are co-prime, this is equal to 1. So when we put the value here, so only we will left with those primes which are co-prime to k. And for those primes this is 1, so we will cut this term. So this summation is summation chi1 p log p upon p. For those primes which are not co-prime to k, this term is 0, and for the primes which are co-prime to k, this is 1. So this summation is equal to just summation p less than equals to x, p and k are co-prime, log p upon p. So now this summation is split into these two summations, summation log p upon p over all the primes minus summation log p upon p over those primes which divides k, because p is a prime and p will be co-prime to k only if p divides. P will be co-prime to k whenever p does not divide k. So we will subtract from whole of the sum we will subtract from whole of the sum corresponding to the primes which divide k, because all other primes which does not divide k, they are co-prime to k. So since we have only a finite number of primes which divide k, because k is a fixed integer, so this term becomes just order of 1, because this term is actually sum of log p upon p, and we know log p upon p, this is a term which is less than 1. And this sum contains only a finite number of terms, because there is only a finite number of prime divisors of k. So we have finite sum of the terms which are less than 1. So this term can be written as order of 1. So the first term on the right hand side of this equation 7, that becomes just this summation log p upon p over all the primes, p less than equals to x plus order of 1. So we will combine this with our equation 7. So equation 7 becomes, because of this, now equation 7 becomes here 5k summation p less than equals to x, p is congruent to h modulo k, log p upon p is equal to summation log p upon p over the primes plus order of 1, that will be our first term, and then second term as such. Summation r varying from 2 to 5k chi r bar h, summation over the primes chi r p log p upon p plus order of 1, and this proves the lemma 1. Because on the left hand side we have 5k, and when we divide whole equation by 5k we will get the lemma 1, so which completes proof of lemma 1. I will give the proofs of all other lemmas in the next video.